Hello, welcome to the lecture on quadratic inequalities. All right, suppose we had a quadratic function like the one graphed here, and we're interested in all the values of that function that are positive, right? Or we're interested in all the outputs of the function that are greater than 0. In that situation, when we have the graphical representation of a function like we do here, the portion of this graph that would show us all the function values that are positive would be the portion that is above the horizontal or the x-axis, right? And because the outputs of a function refer to the y coordinates of any point on the graph of that function. So everywhere that this graph is pink, the function itself, f of x, or the output of that function, is greater than 0, okay? And also all the y coordinates of any points on the graph of that function are going to be greater than 0. All right? Conversely, if we were interested in everywhere that that function was negative, we would be interested in the blue portion of the graph down here, right? We would say that's where f of x is less than 0, or where all the y coordinates of any points on that graph are less than 0. Okay, so this example here says, based on the graph of this quadratic function, find the set of all x values for which the points, any point on the graph with an x and y coordinate, the points are on the graph and y is greater than 0. Okay, and to your answer using interval notation. All right, so for this particular graph, this is kind of a very specific way of saying where is that function positive, or where is that function greater than 0. All right, well, that function is greater than 0 everywhere the graph is pink. So all the x values of those coordinates in interval notation, let's see, the smallest x value, x's are left to right. The smallest x value is going to be negative infinity. All right, and y is positive all the way up until this point right here, and y crosses over the x-axis. Y crosses over the x-axis and becomes negative. Okay, so we don't want to include this portion of the graph. We don't want to include these x values, right? So we want to stop at 3, or x equals 3, that's right there. But we want this portion of the graph as well, so the first interval will be in union with the interval that picks up again right here where x is 6 off to infinity. All right, so when we're interested in where a quadratic function is greater than 0, it's the portion of the graph that's above the x-axis. Where the quadratic function is less than 0, it's the portion of the graph below the x-axis. And we always refer to the intervals, or the solutions, we always refer to the solutions of a quadratic inequality as intervals of x values, right? So these are x value intervals. All right, now that doesn't seem too bad, does it, when we have a function in its graphical form? We want to know what's positive, we go above x-axis, what's negative is below. What if we had just the algebraic representation of this function? All right, if we didn't have the graph, how would we go about solving the inequality? Well, let's look at another example. Let's do this. Look at another example. Here we have an inequality, x squared plus 7x plus 6 is greater than 0. All right, we want to solve the inequality here. So that's another way of saying that we're looking for the intervals where this quadratic function is positive, where this quadratic function is, look, greater than 0. All right, so if we're going to solve that quadratic inequality, how would we go about doing that? Well, we know how to solve quadratic inequalities, right? So the first thing that we want to do here is let's just change that inequality into an equality and go ahead and solve it that way, right? So if we do that, let's see, let's write it as an equality. X squared plus 7x plus 6 is greater than 0. I'm sorry, is equal to 0. We're going to change that into an equality is equal to 0. So what will we want to do here? Well, if it factors, we could solve it that way. And this one does factor. All right, that's going to factor into x plus 6 times x plus 1. All right, then we can use the zero product principle to say either x plus 6 equals 0 or x plus 1 equals 0. Subtracting 6 from both sides, we see here that x would be negative 6. Subtracting 1 from both sides, x would be negative 1. So there's the two solutions to the equality, but we were actually dealing with an inequality, right? Not an equality. So what do these numbers tell us here? What do these numbers tell us here? Well, let's see. If we were to graph this function, it would look something like this. Let me put the graph. I'm going to just put a rough sketch of that. Let's see. This is an upward opening parabola, right? It's not in this parabola form, but it's going to look something like this. This is just a rough sketch, okay? You could graph that in Desmos and look at it to get a better idea, but it's going to look something like this. And what ends up happening here is, of course, when we're solving an equality, we're looking where the quadratic function is equal to 0 or where the y is equal to 0. So this value here is negative 1, and the value over to the left would be negative 6. Okay. So if we set this inequality up as an equality and solve it, what we're looking for is where that quadratic function intercepts the x-axis. So if we were graphing it, we would know we're interested in greater than 0. We would know that the portions of the graph that we're interested in would be these portions here, right? However, can we know this without graphing it? Sure, we can. And what we can do to find this portion of the domain where the function is positive is to go ahead and test some values. So we might make a number line here. We know that at x equals negative 6, the graph intersects the x-axis, and at x equals negative 1, the graph intersects the x-axis. And so what we're doing here is we're dividing this number line up into 3 areas. Okay, now we have that graph, so we know it's the area to the left of negative 6 and the area to the right of negative 1 that are going to be where that quadratic function is positive. But if we didn't have that graph, it might be at the two ending intervals, or it might be this middle interval. We can see this is upward facing, so intuitively we would say, oh, it's probably these outer intervals. But there's a technique that we can use algebraically with just testing some values. If any value less than negative 6 makes that inequality true, right, then that's going to be an interval that we want. If any value in between negative 6 and negative 1 makes that inequality true, then that's an interval we want. Or if any value greater than negative 1 makes the inequality true, that would be an interval that we would want. So what we'll do is we'll just test each interval. Let's just pick some values to test. How about in this interval to the left of negative 6, how about if we just pick negative 7, since that's a smaller number that's in the interval. So to test negative 7, let's see, I want to plug it back into the inequality and see if it makes the inequality true. I think what I'm going to do is I'm going to use the inequality in its factored form, right? So let's rewrite x plus 6, x plus 1 is greater than 0. Okay, that's just our quadratic function factored. It's just easier to test it that way, right? If we plug in negative 7 for x, we get negative 7 plus 6, or negative 1, times negative 7 plus 1. That's times negative 6. Well, negative 1 times negative 6 is greater than 0, right? It's positive 6, and 6 is greater than 0, so this is an interval that's good. This is an interval that we want. All right, then we might test a value in the middle interval here. Let's try negative 2 just because it's an easy number to deal with. Any value in that interval will work. If we test negative 2, well, let's see, negative 2 plus 6, that's going to be positive 4. Okay, times negative 2 plus 1, that's going to be negative 1. And negative 4 times negative 1 is negative 4. And look at that, negative 4 is not greater than 0. So this interval in here is one that I don't want. Since that value, since that value of negative 2 did not satisfy the inequality, that interval, that orange interval, is one that we don't want, whereas the purple interval was one that we did want. And then there's one more interval we should test. That would be all the values greater than negative 1. Maybe we'll use blue for that interval. And maybe we'll use the value of 0 as an easy one to test, and that would be in the interval of all values greater than negative 1. So if we test 0, we would say 0 plus 6, or 6, times 0 plus 1, 1 is 6 times 1. That's positive 6. Again, positive 6 is greater than 0, so that is a good interval. That's an interval that satisfies this inequality. It's one that we want. All right, so if we were to write this in interval notation, we of course want all the values less than negative 6. So we would say negative infinity up to negative 6 in union with all the values greater than negative 1, negative 1 to infinity. All right, and I'm using the parenthesis here instead of a square bracket because it's not greater than or equal to, it's just greater than. Okay, so there was a procedure that I actually followed here, and I have that summarized for you. Here's a summary of the procedure that you can use to solve a quadratic inequality. If the inequality isn't in standard form, you'll want to move all the terms to one side. All right, then go ahead and factor it if you can. If you can't factor it, you'll have to use the quadratic formula. Right? Then make that inequality an equation, solve to find the boundary points for the solution sets, right? You're looking for, when you solve that equality, you're looking for the x-intercepts, right? You're looking for these two values here because that's going to tell us the intervals above the x-axis and the intervals below the x-axis. Okay? Mark them on the number line and then test the intervals. Pick an easy number that's in each interval. Test the interval to see if it makes the inequality true. And then go ahead and write it out in interval notation. All right, shall we look at another example? Let's do another one. Okay, this one's not in good form yet, is it? It just looks, everything's everywhere. In fact, at a first glance, you'd think maybe it's not even quadratic. I don't see an x squared anywhere. But if I were to solve any inequality that wasn't simplified, I'd want to simplify it first. So we'll need to distribute that 3x so we can drop those parentheses. So 3x times x is 3x squared, and 3x times negative 1 is negative 3x. Okay, and that'll be less than or equal to the 10 minus 2x. Okay. Now, if we're thinking about our procedure here, we want to put it in standard form, or the first step says move all the terms to one side. All right, so we'll do that. We'll add a 2x to both sides, and we'll subtract a 10 from both sides. So we'll have 3x squared, negative 3x plus 2x is negative x minus 10. And that will be less than or equal to 0. Nothing left on the right-hand side. Okay. Now we want to go ahead and factor this if we can, because what we want to do is to make it an inequality and solve it, right? So step 2 says factor. Let's see if it will. Will this one factor? Let's see. We'll have to use the AC method here, right? So A times C, that's 3 times negative 10, or negative 30. All right, we want factors of negative 30 that add to negative 1. So I think that that's going to be 5 and negative 6. 5 times negative 6 is negative 30, right? And 5 plus negative 6 is negative x. All right, so we're going to split that middle term into those factors. So we'll have 3x squared plus 5x minus 6x minus 10. All right, let's group. Pull out the greatest common factor. Here it's just going to be an x. We're left with 3x plus 5. Greatest common factor of negative 6x minus 10 is going to be, let's get a negative 2 out of there. So minus 2, we're left with a 3x plus 5. All right, so we have 3x plus 5 remaining, both portions. So let's factor that out. So then we have 3x plus 5 times x minus 2. And we were saying that was less than or equal to 0. All right, now that it's factored, let's make it an equality and solve. And we'll make it an equality and solve. So we'll say 3x plus 5 times x minus 2 is equal to 0. Then we'll use the zero product principle. So either 3x plus 5 equals 0, or when we subtract a 5 and divide by 3, x equals negative 5/3, right? Or x minus 2 equals 0, add 2 to both sides, x equals 2. All right, so there's our two solutions. What do we just find here? We just found the x-intercepts, right, or the horizontal intercept for this parabola if we were to graph, right? If we were to graph that quadratic function. So if I were to graph it, it would look something like this, right? Here's our x-axis, our y-axis. It's going to intercept, let's see, this is an upward opening parabola. It's going to intercept the x-axis at negative 5/3 and x equals 2. All right, so this parabola is something like this. I don't really know where that y-intercept is, but it's going to look something like that because it's upward opening, right? A is positive, opens up, and it has these x-intercepts. Now, to continue to find my intervals where this graph is less than or equal to 0, right? If I hadn't graphed it, I would make my number line. Okay, where am I in my procedure now? Let's see. I'm solving to find the I found the boundary points. We solved already, and now I'm going to mark these points on the number line. All right, so here's my number line. We'll say negative 5/3 is here. We'll say 2 is here, and here's my 3 intervals. Okay, now I want to pick test values and see if they satisfy the inequality. All right, so let's see. Maybe we'll do the first interval here. A test value, maybe we'll use negative 2. Okay, let's test negative 2. I want to use this version of the inequality because it's factoring easier for me to deal with, right? So if I'm testing, I'll just write it here, x equals negative 2, 3 times negative 2 is negative 6 plus 5. Well, that's a negative 1, right? Times negative 2 times negative 4, and negative 2 minus negative 2, that's negative 4. Well, negative 1 times negative 4 is positive 4, and 4 is not less than or equal to 0. That's not true. That means my purple interval here is not a good interval. It does not satisfy the inequality. All right, so I throw that one out. Let's test, and does it make sense? Yeah, look, the purple portion of my graph, if I graphed that, would have been this part here, right? And that part there is not less than or equal to 0. I don't want that part. The middle part should work, shouldn't it? That's the part of the graph that's less than 0. That's the part of the function that should be less than 0. Let's test the middle part, pink on that part. So let's test this interval here. 0 is in that interval, and that's a nice test value. So let me use that one. Maybe I'll click next, but this is actually a bad interval. I want X on the whole thing, a bad interval. I don't want that. All right, so if X is 0, if we test that, 3 times 0 is 0 plus 5, which is 5. And then 0 minus 2 is negative 2. 5 times negative 2 is negative 10. Negative 10 is less than or equal to 0, right? So that's a good interval. As expected, the purple portion of that graph, or the pink portion of that graph, or that pink interval, is one that satisfies the inequality. It makes it true. I'm using this factor version. So I want to keep that interval. All right, we have one more interval to test. We'll do that one in blue, this interval here. Maybe we'll use the value of X equals 3. All right, so let's test X equals 3. 3 times 3, that's 9, plus 5, that's positive 14, times 3 minus 2, that's positive 1. 14 times 1 is 14, and 14 is not less than or equal to 0, not. So this is not a good interval. This interval does not satisfy our inequality. All right, so here's our solution. It's the pink portion here. Our solution then is going to be from negative 5/3 to 2. And this time, look, since it's less than or equal to, see, I've got the or equal to going on there. I want to use the square boundaries, the square brackets to indicate that those boundary values must be included in the interval because it's or equal to, it's less than or equal to the value. All right, let's do another example. It can be rather complicated, huh? Let's try another one. I'm not even going to draw the graph of this. I'm just going to use the procedure. Well, when I look at that first, I see that it's not in the right form, right? So I'm going to move all my terms over so that it's got 0 on one side. So I'll subtract that 8x from both sides, and I'll have 2x squared minus 8x plus 4 is greater than 0. Okay, now that it's in the right format, let me see if that's going to factor. All right, if I pull a 2 out and a 2 and 4. Okay, this one's not going to factor. So how will we go about solving this? How will we go about solving this? Well, I'm going to have to use the quadratic formula, right? I'm going to have to use the quadratic formula, and I could make it a little bit easier. I could have smaller numbers to deal with because, look, I can factor out a 2. Let's factor that 2 out to make this a little easier. So this will then be 2 times x squared minus 4x plus 2. There. In fact, if I want, I can just divide this 2 away and not even have to think about him anymore, right? All right, so now I have x squared minus 4x plus 2 greater than 0. This will not factor, so I'm going to use the quadratic formula here. Let's put it up here. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a, okay? And a, on our quadratic inequality here, a is 1, b is negative 4, and c is 2. Okay, let's plug those in and solve for x. So negative b, that'll be the negative of negative 4 plus or minus the square root of negative 4 squared minus 4 times a, that's just 1, times c, that's 2, all over 2a. That's just 2 times 1. Okay, so this is then 4 plus or minus 16 minus 8, so that's the square root of 8 over 2, or simplified, that's 4 plus or minus 2 square roots of 2 over 2. Further simplified, that's just going to be 2 plus or minus the square root of 2. All right, there's my two values. Let's approximate them so we can see kind of where to put those on the number line. Okay, 2 minus the square root of 2 is 0.586. 2 plus the square root of 2 is 3.414. So there's my two values. Let's put those on the number line to divide up our intervals. We'll say 0.586 is here and 3.414 is here. Okay, so let's test those intervals now. Let's see, our first interval here, we'll say that's the purple interval. We'll use 0 because that value is in there. All right, so let's test 0. We don't have a factored version to use this time, so we're going to have to use the initial version of it, right? That's fine, we can do that. All right, so we'll test x equals 0. If x is 0, 2 times 0 squared minus 8 times 0, that's 0 minus 0 plus 4. 4 is definitely less than 0. So that looks like this is an interval that I want to keep. Okay, let's test that middle interval there. The value of 1 is in there. Let's test 1. Okay, so if x is 1, 2 times 1 squared, that's 2 minus 8, that's negative 6 plus 4, that's negative 2. That is not greater than 0, so I don't want that middle interval. Now let's test this last interval here. Let's use the value of 4 to test that interval. If x is 4, let's see, 2 times 4 squared, that's 32. 2 times 16, 32 minus 8 times 4, that's 32 minus 32. So we're just left with 4 is greater than 0. That looks good. 4 is greater than 0, so that's an interval that I want. Okay, so my solution here then is going to be negative infinity to 0.586, or if I want the exact answer, I could say 2 minus the square root of 2 in union with 2 plus the square root of 2 out to positive infinity. So negative infinity to 2 minus the square root of 2 in union with 2 plus the square root of 2 to positive infinity, if I want to put this in exact form. Okay, does it make sense graphically? I can always graph this in, I can always graph this in Desmos to check it out. I could do that, or I could just think about what I know. This is an upward facing parabola, right? And I would do rough sketch, that's upward facing because A is positive in factored and unfactored versions. A is positive, so upward facing. So I think that it makes sense. It's got an x-intercept at 2 minus square root of 2 or 0.586. Right there, 2 plus square root of 2 or 3.414. So it's, I don't know, a parabola that's something like that. It's going to be positive. It's going to be positive up here above the x-axis. And I was looking for greater than 0. I was looking for the positive parts. So, yep, I think that makes sense. Okay, should we do another example? Let's do one more. Why not? Okay, here's another one. It's not in the right format yet. Let's put it in the right format. Okay, so we'll move everything over to the left. Negative v squared plus 3v minus 7 is less than or equal to 0. All right, and I might try to factor that. I might factor out the -1 first. Let's see. V squared minus 3v plus 7. It's easier for me to factor when the leading coefficient is positive. But there are no factors of +7 that add to -3. So that means that I'm going to need to use the quadratic formula. Okay. I'm going to look at it in its original form, so we don't need that anymore. So here, A is -1, B is 3, and C is -7. So that means V has to be -B, or -3 plus or minus the square root of 3 squared minus 4 times A, -1, times C, -7, all over 2A. Let's see, what is that? -3 plus or minus the square root of 9 minus 28. What is that? -19. All over -2. That's kind of weird now, isn't it? Look at that. We have a negative radicand. What does that mean? Negative radicand. That's not a real number, is it? I need to introduce I, right? I would write this as -3 plus or minus I square roots of 19 over -2. Well, how do I put that on the number line to test my values if it's not a real number? I can't. I can't put that on the number line. I don't know where imaginary numbers are on the number line. I would need an imaginary number line for that, wouldn't I? I can't put that on the number line. So what do I do with this one? Well, when there is no real solution, right? No real solution. Okay, there's no real solution, the key word being real here. When there's no real solution, that means there's no x-intercepts. No x-intercepts of the parabola. If you were to graph that parabola, there's no x-intercepts. Okay, so think about that. What might that graph look like without doing it very carefully? I could just, I don't know, I could say, well, it's downward facing, right? Downward facing. It needs to be less than 0. I mean, I don't know offhand if it's left or right, but it's going to be something down. Probably here. It's going to be down here like this, right? It's going to be below that x-axis. It's downward facing. It doesn't have any x-intercepts, so it's going to be something like that. So what does that mean? If there's no real solution, either all x values or all, the whole parabola, all the y coordinates and x, everything is below the x-axis. The whole thing is less than 0, or the whole thing is greater than 0. Well, we know this is a downward facing parabola, so we know that this whole thing is going to be less than 0. That we know that any x value is going to give you a negative y value, right? So to solve this, I can graph it and see it that way, or I could say if there's no real solution, that means there's no intercepts. Then I could say that means test any value. Test any value at all. 0 is a nice one. So let's test x equals 0. Do it here. X equals 0. Well, let's see. -0 squared, that's just 0 plus 3 times 0, 0 plus 0. So this is just going to be -7 is less than or equal to 0. Is that true? Yes, it is. Yes, it is. That means that all values are going to be a solution here. So my answer is going to be -infinity to +infinity, right? That's the solution to that quadratic inequality. All values of v, this is a v-axis here, instead of x's and y's, we're using v's, right? All values of v are going to result in negative outputs of the function, right? Negative outputs of the function. So -infinity to +infinity, or we might say all real numbers. or sometimes we even use this symbol like this. Okay. All right. So to summarize, when there is no real solution, that means the graph has no x-intercepts, because when we set that equal to 0, what we're doing is we're finding the x-intercepts, right? Or v in this case. That means there's none. So we can test any value to see if it's true. If it is, then the answer is going to be all real numbers. What would have happened if 0 hadn't made this inequality true? Well, then we would have had to say there's no solution. Let's look at one more example. Spoiler alert here, right? Let's look at this example. Here we've got negative j squared plus 6j is greater than 10. All right, well, let's put it in standard form. Move everything over to the left. Negative j squared plus 6j minus 10 greater than 0. Greater than 0. Okay, and I might try to factor that, but I would quickly see that that does not factor. So I'll use the quadratic formula. So A is -1, B is 6, C is -10. So that means X, or in this case, we're doing J. J is going to be negative B plus or minus the square root of B squared minus 4 times A times C. That's -10. All over 2a, that's 2 times -1. Simplify, that's -6 plus or minus the square root of 36 minus 40, or -4 over -2. Now simplify more to -6 plus or minus 2i over 2, or -3 plus or minus I. Okay? So we have no real solution here. There's an I, right? No real solution. No real solution. So J can be either all reals, all real numbers, or no solution at all. To find out which one, test any value. We'll pick 0. It's the easiest one to test. So we'll test j equals 0. Let's plug it into our inequality and see what happens. Negative 0 squared, that's just 0, plus 6 times 0, that's 0. So negative, that leaves us with -10 greater than 0, and that is not. -10 is not greater than 0. And since it's not greater than 0, we want to say that this particular inequality has no solution. Okay, or we might say it's the empty set, like that, or we might even do it like this. No solution, or one of the symbols for the empty set. Okay. What would this look like if we graphed it? Well, it's a downward facing parabola. Look, A is -1. It's a downward facing parabola. Can a downward facing parabola always be entirely greater than 0? No, it can't be. It makes sense, right? Because downward facing parabola, it's got to go like this. No matter how high up I put that parabola, the ends are eventually going to get down below the horizontal axis, right? And only this part's going to be true. There's going to be, or only this part above here is going to be true. There's always going to be some part of this parabola below the x-axis. All right, this ends the lecture on quadratic inequalities.